Hello everyone. Today I'll be presenting our work on a clustering-based selection framework for cost-aware and test-time feature elicitation, abbreviated as GATE. I'm Srijita Das, and this is joint work with Rishabh Iyer and Sriram Natarajan from the University of Texas at Dallas. Here is the outline of my talk. I'll first motivate the problem, followed by the problem setup and formulation. Next, I'll present the experimental results, followed by conclusion and other future work. Coming to the motivation of this work, let us imagine a clinical setting where the task is to predict whether a person has diabetes or not. In such a setting, there can be various range of features. One set of features are the demographics like age, gender, ethnicity, zip code, etc., which are reasonably easier to collect and cheap, and they incur zero cost in our setup. These features are called observed features. The other set of features are the ones related to image data like MRI scan data, X-ray, or other kind of lab tests or human genotype data, which are more cumbersome to collect and incurs cost. So these features are called elicitable features in our problem setup. The question that we are trying to answer in this work is, at prediction time, if a new person comes with some of the features like the demographic features observed, whether we can identify what are the most important elicitable features for that person in order to predict whether the person has diabetes or not. This problem is extremely important because firstly, the person might have budgetary constraints and might not want to carry out unnecessary lab tests or other lab procedures. Secondly, imagine a scenario for the hospitals in times of COVID where they would not want to waste their resources by carrying out unnecessary lab tests. We have some assumptions. The first assumption is that the training data is fully observed, which means for training data, both the observed and the elicitable features are available and doesn't incur cost. The test data is partially observed, which means that at test time, the observed features are available and the elicitable features are not available and they come at a cost. Elucidating more on the intuition for GATE, which is our proposed approach, we build on this very simple intuition that people with similar demographic are more likely to have similar elicitable features. Hence, at training time, if we can identify these various clusters in the data based on the observed features, which are easily available, uh, and if we can identify the important elicitable features for each of these clusters, then at prediction time, if a partially observed instance comes with these features like age, gender, ethnicity, zip code, etc., all we have to do is map this person to the nearest cluster based on these features, and then elicit the important features which are required for that cluster. Moving on to the problem setup and formulation. Here is the problem setup. We are given a typical supervised classification setting where each instance is characterized by a feature vector and their corresponding labels. We are also provided a cost vector which specifies the feature acquisition cost for each of the elicitable features. And then there are two types of feature sets as already discussed, the observed feature set and the elicitable feature set. What we want to do, we want to learn a discriminative function G, which is capable of managing this trade-off between feature acquisition cost and the model performance. And it should also elicit the important elicitable features for this partially observed test example at prediction time. The assumptions that we have is that the observed feature set has zero cost, and this feature set is available for all the examples, which means it's available for both the training and the test examples. And the elicitable feature set incurs cost, and it is available just for the training data and is not available for the test data. Moving on to the related work, this problem has been looked in literature from various directions. One of the direction is along tree-based budgeted learning, where the feature acquisition cost is typically added to the splitting function for growing a decision tree or other ensemble-based methods in order to manage this trade-off between acquisition cost and performance. There has been a line of work along adaptive classification, where typically high cost model is used to learn a function, and then a low cost model is used to selectively approximate this high cost model wherever possible. Reinforcement learning approaches has long been used to address the problem of test time feature elicitation. In such approaches, the action set is typically whether to acquire a feature or not, and policy is typically the ordering in which various features are acquired for a particular instance, as well as when to stop acquiring those features. However, this direction, like the reinforcement learning approaches, are pretty computationally exhaustive. There is another line of work along active learning, which deals with feature acquisition in an active learning setting. So some of the work along these direction are similar in setup to our proposed approach, but they deal with an active learning setup, whereas we are more in the supervised learning space. Moving on to our proposed framework. So we try to look at this test time feature elicitation as a two-level optimization problem. So this is our framework, where the first step consists of a clustering step, which clusters the training data based on just the observed features and forms these M clusters, C1, C2 up to CM. Once these various clusters are identified, what the feature selector module does is it optimizes a particular objective function, which I'll address in my next slide, and identifies the important elicitable feature for each of these clusters. And once that is identified, the model optimizes a typical loss function using just the elicitable features along with the observed feature set. So the interesting thing here is that not all the features are used for the model optimization part, but just the elicitable features and the observed features are used. And this loss function is pretty general, and it can be anything ranging from log likelihood to squared loss, depending on the task at hand. Our method is knowledge intensive in the sense that, firstly, the observed and the elicitable feature splits can be provided by the human expert, as well as the various feature acquisition cost can be provided in our framework using human guidance. Now, coming to the feature selector part, this is the feature selector objective function, which is defined for every cluster I, and it consists of 4 different terms. The first 3 terms are information theoretic measures. So if you look at the first term, this is what is called max relevance, and it is the mutual information between every feature in the selected subset S and the class variable Y. And we know that for a discriminative task, a good predictor variable is highly correlated with the class variable. Hence, this particular term needs to be maximized in the chosen feature set. The second term is the correlation between pairwise features in the selected subset S. And this needs to be minimized because we know that if 2 features are highly correlated among themselves, one of them is redundant and do not add any value as such. The third term is called conditional redundancy, and this is the mutual information between every feature and this class conditional variable, and this needs to be maximized. And the last term is the cost penalty, which kind of specifies the feature acquisition cost for the chosen features in the subset, and this is added as a penalty term, and this term kind of manages the right trade-off between acquisition cost and performance. We grow the subset S using a greedy optimization strategy, where we start from an empty set and at every step add the feature from the elicitable set, which gives the maximum gain with respect to this particular objective function. Moving on to the optimization part. So the feature selector optimization function selects the best subset from the elicitable set, which maximizes this particular objective function, as already discussed previously, for every cluster. And once this feature subset is identified, the model optimization uses just the elicitable subset along with the observed set and optimizes the loss function. And this objective function also has the feature acquisition cost of the particular selected subset, along with the typical regularization component, which is used to prevent overfitting. Moving on to the experimental evaluations. Data sets are partitioned into 80% train and 20% test. The various hyperparameters like number of clusters and the regularization coefficients are chosen using five-fold cross-validation. We report metrics such as recall, F1 score, AUC, ROC for imbalanced data sets and accuracy for balanced data sets. And SVM with radial basis function are used for prediction. These are the baselines that are considered. So OBS is predictive task using just the observed feature set. R&D is the predictive modeling using observed set and randomly choosing the elicitable feature subset. K-best is a non-clustered version of our algorithm where we use the same objective function to select the K-best features for all the training data, and then they're used for predictive modeling. And AdaptLin is one of the state-of-the-art approaches introduced by Nan et al. For adaptive classification, and we compare our algorithm against theirs. These are the experimental results using hard budget on features. We consider two variants of Kate. The normal Kate is the one where the not important elicitable features are imputed with 0. And for Kate I, we use an imputation strategy to impute the unimportant elicitable features. And we compare this against the baseline approaches. And for hard budget, we consider uniform cost on all the features, and we keep the number of elicitable features fixed, which is chosen by cross validation. And we see that our method performs better than the other baseline approaches. Moving on to the cost version of Gate. In this version, we put non-uniform acquisition cost on the features and evaluate the cost version against the other baselines. And here also we see that on most of the data sets, Kate performs better than the other baseline approaches. For ADNI, we see that Kate performs better than the other baseline approaches in this middle zone. And this is mostly because in this middle zone budget, the maximum diversity in features is obtained. We also compare Kate against AdaptLin, and we see that it performs better or at par with AdaptLin for most of the data sets. Moving on to conclusions and future work. To conclude, we propose a test time feature elicitation algorithm, which kind of uses this feature selection and model together to rightly trade off between feature acquisition cost and the feature acquisition cost and the model performance. As future work, we want to jointly learn the parameters of the feature selector and the model. Right now, the parameters of the feature selector are kept constant for this work. We also want to pose this as a submodular optimization problem, and we want to add more robust constraints to the optimization problem. Also, one of the assumptions for our work is that the training data is fully observed, and like both the observed and the elicitable features do not incur cost while training. We want to go ahead and relax this assumption in our future work. That's all from my end. Thank you so much for your time.